Hey guys, the first lecture of ELEC 2607, part 1 of part 3, and we're going to be going over the basics of Boolean Algebra. The very first two things you guys have to know is true is also dictated by 1 or high, and false is dictated by 0 or low. And that can be seen over here. So the very first logical operation you can do is not. All this states is this A is equal to 1, not A is equal to 0. And vice versa, and states that two things must be true for the whole equation to be true. So A is 1, B is 1, then X, or the outcome, is 1. However, if any of these change to 0, X becomes 0. Or states either A or B must be 0, or B, must be 1. So if A is 1 and B is 0, that's okay, X is 1. That's okay, X is 1, that's okay, X is 1, but this is the only time where it's false. Boo! Alright, next we have XOR. XOR is similar to OR, except that only A or only B can be 1 in the combination. So over here, this would be true because only A or only B is true. This would also be true. However, this is going to be false as they are both 1, but you only need one of them to be 1. Then you have your combination of not and not or, and not XOR. Not and, you have to be careful where you have to do the and part first and then the not part. And this goes for the same as not or and XNOR. So, if A is and B is true, that would be false. And then if A or B was true, that would be false. And if A XOR B was true, that would be false. Alright, so now we actually got to look at some truth tables, which are these guys over here. The way you construct a truth table is first you have your inputs. So let's say you have A, B, C, and X is your output. So you have all your inputs. I'm just going to do 3 for the sake of this example. So you have 0, 1, 0, 0, 0, 0, 1, 1, 1. Alright. And let's say the logical operator is AND. A and B and C. Well, what we do know about this is that all of them must be 1 for X be 1. So let's put one more. So the only one that will be true is this one, and these ones will be false. Here is your truth table for these. So we actually wrote a bunch of useless stuff, and that's where the negative sign, hyphen, minus sign, or negative sign comes into play. This stands for doesn't matter, or either or. Either or. So, since we know that all of them must be true, A, B, and C must be true, if as soon as you see a 0, instead of writing 0 or 1, you can just put negative signs, because it doesn't matter if this is 0 or 1, the whole thing's going to be false. And you could do that everywhere you want. Okay, and then you have the compact truth table, which looks like this. You have your inputs like that. So here are your inputs for B, and here are your inputs for A. It's like a multiplication table. The output goes into here. That is not a 0, that's a circle. So 1 and 1 will give you true, 0 and 1 will give you false, assuming it's A and B. That will give you false, that will give you false. So 1 and 1 will give you 1, 1 and 0 will give you 0, and so on and so forth. Also, these are your schematics. This is how you represent it using circuits and diagrams. I can't teach you anything conceptually about this, but you actually have to memorize them, as there's a couple of problem questions that he did provide us. Again, these are schematics with these guys. Again, please do memorize these. And finally, these schematics as well. Everything on over here, you can work it out by yourself. There's nothing conceptual about those. Alright, now this is also another important thing you probably want to memorize or at least understand. I will be showing you an example of a couple of these guys. So for example, this one. This is stating, here, let's rewrite it over here, x or 0 is x. This is true because for something to be true when it's OR, there needs to be one true value. Since you already know that this is false, everything is dependent on this guy, hence why this whole thing is x. Like similar to that, since OR needs only, oops, that's a OR now, since only one thing needs to be true, you already have the 1 over here. So it doesn't matter what x is. If x was 0 and it was 0 or 1, and then you would have 1. So everything is dependent on the 1, hence this one is true. And don't worry about this column, that will be in the next video where we go over dual. And you also have the double negative. Well, you know, it's similar to this. Take the negation and the negation of 1. So you take 1, negate it twice, well, you're left with 1. The idempotent rule states x or x is x. Well, both of these are dependent on x, so same thing as x, isn't it? Your commutative law is simply 2 plus 3 is equivalent to 3 plus 2. Your associative law states it doesn't matter which way you add them or them in this case. And distributive law is just like in math. Alright, so what happens if you have a proof? For example, they say prove A or C and B or C is equivalent to A and B or C. You can use the exhaustive method. It's called exhaustive method because it's rightfully so. You have to take every single possible input, calculate every single part together, calculate the whole left side, and repeat everything for the right side. Now this way is long, but it is so hard to screw up on this, and that's why it's sometimes recommended, but only if you have time, because this does take a while. Again, you have to write 8 times 1, 2, 3, 4, 5, 6, 8 times 6, which is 40. You have to write 48 characters out, and that is really annoying. But thankfully, there's a compact truth table, as I showed earlier, and I'll show it again. In this case, you can draw it like this. And that makes 48 down to about 24, and that is super awesome. Alright, that sums up everything for part 1. I'll see you guys in part 2, where I take a look at duals.